Okay, in this lecture we're going to cover our section 5.2 material on the characteristic equation, which will give us a way to determine the eigenvalues of a square matrix. So in our last section we had introduced the concept of an eigenvalue or eigenvector of a matrix, and we saw that if we're given a specific scalar or a vector, it's easy to determine whether or not it is an eigenvalue or an eigenvector of a square matrix. But the question is, how do we find those eigenvalues or eigenvectors from the matrix? So that's what we're going to be considering in this section. So to introduce the idea, recall the definition of an eigenvalue and vector. We would say that a scalar lambda is an eigenvalue of a square matrix A, say an n by n matrix, if there exists a non-zero vector x such that A times x is equal to lambda times x. And in this case, the vector x is called an eigenvector of A corresponding to that eigenvalue lambda. So as we saw in our last section, the equation in the definition of an eigenvalue and vector, ax is equal to lambda x, can be rewritten in the form a minus lambda I times x is equal to 0. So a little review of how that works. If we have ax equals lambda x, we can subtract lambda times x from both sides, and we would have ax minus lambda x is equal to the 0 vector. And so factoring out an x, we have a minus lambda, which we have to multiply by the identity matrix so that we can subtract this quantity from the matrix A, all times the vector x is equal to 0. So that is the equation which we have here. So to find an eigenvalue, we need this equation to have a non-trivial solution. Recall the definition of an eigenvector is that it has to be a non-zero vector that satisfies this equation. So we would say lambda is an eigenvalue of A if and only if this equation has a non-trivial solution. Now this is a homogeneous linear equation or system of equations, which we know will have a non-trivial solution if and only if the coefficient matrix A minus lambda times I is not invertible. Now, our usual check for whether a matrix is invertible is whether it has a 0 determinant or not. So in order for this matrix to be not invertible or singular, the determinant of that matrix, A minus lambda I, has to equal 0. So this equation gives us a method for solving for our eigenvalues lambda. We know for any square matrix we can expand this determinant, perhaps using a cofactor expansion, and what we obtain is an nth degree polynomial of lambda, where n is the same as the number of rows or columns of our matrix. So when we expand this determinant, this nth degree polynomial of lambda, we might denote as p of lambda, which is defined as the determinant of A minus lambda I, and we find our eigenvalues by setting that equal to 0. So we find here this equation, which we're trying to solve, is called the characteristic equation of the matrix A, and the polynomial p of lambda is called the characteristic polynomial of our matrix. So when we're talking about the title of this section, the characteristic equation, we're talking about the equation that arises from setting the characteristic polynomial of a matrix equal to 0. And so the eigenvalues of a square matrix can be found as the roots of the characteristic polynomial. So let's look at some examples where I'll give you a square matrix and I'll ask you to determine its eigenvalues using the characteristic equation. So in our first one, we're told to find the characteristic polynomial and the eigenvalues of this 2 by 2 matrix A. So recall our characteristic polynomial is the polynomial defined as the determinant of A minus lambda times the identity matrix. So recall, as we saw in the last section, if we take lambda times the identity matrix, well, we're looking at lambda times the matrix 1, 0, 0, 1, if we're talking about a 2 by 2 matrix. So that is the matrix which has lambdas on the diagonal and zeros elsewhere. So when we're looking at A minus lambda I, we're taking the matrix A and subtracting lambda just from the diagonal entries. The off-diagonal entries, we're subtracting 0. They're not getting changed. So in order to determine our characteristic polynomial, we will let the determinant of A minus lambda I equal to 0. This is our characteristic equation. So let's look at that determinant. So here I'm going to use the vertical bar notation for determinant. And again, to find A minus lambda I, we're taking A and subtracting lambda from the diagonals. So in this case, 5 minus lambda and 5 minus lambda. And from the off diagonals, we're subtracting 0. So we just have the same off diagonal entries. Now for the determinant of a 2 by 2 matrix, we have the product of the diagonal entries, which would be 5 minus lambda times itself, or 5 minus lambda squared, minus the product of the off diagonals, which would be 9. And we're setting this equal to 0. So expanding, we would have lambda squared minus 10 lambda plus 25 and then minus 9 leaves me with a positive 16 is equal to 0. And this quadratic can now be factored as lambda minus 2 times lambda minus 8 is equal to 0. So our eigenvalues are 2 and 8. So this technique allows us, or this characteristic equation allows us to find the eigenvalues of a square matrix algebraically. So for this problem, we found our eigenvalues. Now part of the question asked for the characteristic polynomial, which in simplified form would be the polynomial shown here, this quadratic. So let's look at some other examples. This next one, the exact same sort of problem. Find the characteristic polynomial and the eigenvalues of this matrix. So to find the characteristic polynomial, or the characteristic equation, we're taking the determinant of A minus lambda times the identity and setting that polynomial equal to 0. So let's see what we have using the vertical bar notation for a determinant. We have the matrix 3 minus lambda, negative 4, 4, and 8 minus lambda. So again, we take the matrix A and we're subtracting lambda just from the diagonal entries. So that gives us the following. And taking the determinant of this 2 by 2 matrix, we would have 3 minus lambda times 8 minus lambda, minus the product of the off diagonals would give us a positive 16 is equal to 0. So expanding, we have lambda squared minus 8 lambda minus 3 lambda would be minus 11 lambda, plus 24 and then plus 16 would be plus 40 is equal to 0. So now to solve, we would have if it doesn't factor easily, we could make use of the quadratic formula to find our roots. So here we could take lambda as positive 11 plus or minus the square root of 11 squared, which is 121, minus 4 times a times c. So in this case, 4 times 40, or 160, then all over 2a, in this case 2. So now we are left with lambda equals 11 plus or minus the square root of negative 39 all over 2. So here we would have 11 plus or minus the square root of 39i over 2, where I is the imaginary number square root of negative 1. So in this case, we have complex eigenvalues, which, as we see from this example, is possible for a 2x2 matrix. And we'll discuss complex eigenvalues in more detail a little bit later in Chapter 5. So we see for this equation, our characteristic polynomial, or for this problem, our characteristic polynomial is this quadratic, and we have these complex eigenvalues shown here. So for our next example, exact same sort of question, we are asked to find the characteristic polynomial and the eigenvalues of the following matrix. So to find our eigenvalues, we're taking the determinant of a minus lambda times the identity and setting equal to the 0 vector. So using the vertical bar notation for the determinant, we have the determinant of 5 minus lambda, negative 3, negative 4, and 3 minus lambda. Again, we're just subtracting lambda from our diagonal entries. So this determinant would be 5 minus lambda times 3 minus lambda, minus the product of the off diagonals, 12. And we would set this equal to 0 to find our eigenvalues. So expanding here, we have lambda squared minus 8 lambda plus 15 minus 12 would be plus 3 is equal to 0. And again, in this example, it doesn't seem that this quadratic factors. So if this does not factor, then we could use the quadratic formula or complete the square in order to solve for lambda. And here we would have lambda is equal to 8 plus or minus the square root of negative 8 squared, which is 64, minus 4 AC, in this case is 12, all over 2a. So simplifying, we have lambda is 8 plus or minus the square root of 52 all over 2. But now 52 is 4 times 13, so we have 8 plus or minus the square root of 4, which is 2, times the square root of 13 all over 2, or dividing through by 2, we're left with 4 plus or minus the square root of 13. So here we have real eigenvalues instead of complexes in the last example, and our characteristic polynomial for this matrix was the following quadratic. Okay. So let's look at some examples with larger matrices, say 3x3 matrices. So the procedure is the same. We're going to look at the determinant of our matrix minus lambda times the identity to get our characteristic polynomial, and then look for the roots of that polynomial. So as with our previous example, we would consider the determinant of A minus lambda I, which is the matrix A, with lambda subtracted from the diagonal entries. So the matrix shown here. And we would evaluate this determinant by using a cofactor expansion. So there's a number of ways we could do this. It looks like maybe a cofactor expansion down the second column or the third row would be pretty good because it contains mostly zero entries. So I'm going to stick with a cofactor expansion along my third row. So let's see what the sign is going to end up being. So we start with a plus, minus, plus, minus, plus. So I'm going to start with a positive 2 minus lambda. And then the determinant of the 2 by 2 submatrix that I get by deleting the row and column that 2 minus lambda lies in would give me negative 1 minus lambda times 4 minus lambda minus 0. So I would have the product of these three expressions for my characteristic polynomial. And to find the eigenvalues, we set this characteristic polynomial equal to 0, and we can see that there are three choices. Either lambda is equal to 2, lambda is negative 1, or lambda is equal to 4. Now, of course, you would have the same characteristic polynomial if you did a cofactor expansion along another row or column. So let's consider another one. In our next example, the same problem. Find the characteristic polynomial and eigenvalues of this 3 by 3 matrix. So we're looking at the determinant of this matrix A minus lambda times the identity. So that is the determinant of our matrix with lambda subtracted from the diagonals. So again, to evaluate our determinant of this 3 by 3 matrix, to make this a little more easy, we might use a cofactor expansion across the second row, since it contains mostly 0 entries. And let's see what the sign of our term would be. So we start with a positive, negative, and then a positive 1 minus lambda. Times the determinant of the 2 by 2 submatrix I get by deleting that row and column. So I would have 5 minus lambda times negative 2 minus lambda minus the off diagonal. 3 times 6 is 18, and I'm setting this equal to 0. So expanding within our set of square brackets, we have 1 minus lambda times positive lambda squared minus 5 lambda plus 2 lambda would be negative 3 lambda. Then minus 10 minus 18 is negative 28 is equal to 0. And now this quadratic term can be factored as lambda minus 7 times lambda plus 4 is equal to 0. So we can see now that we have three eigenvalues, 1, 7, and negative 4. And our characteristic polynomial in simplified form would be the following. All right. So let's consider an example of a little bit larger matrix, say a 4 by 4. Now typically when we were trying to find the eigenvalues or vectors of a square matrix, you would use a computer or a calculator to generate those values for any matrix that would be larger than 2 by 2, or certainly for a 3 by 3 or larger, you would want to use software to do this. However, for certain matrices, we can calculate the eigenvalues or the characteristic polynomial very easily. So in this example, we notice that our matrix is upper triangular. And we saw in our previous section that for a triangular matrix, the eigenvalues are exactly the diagonal entries. Now for a little justification of why that's true, not the formal proof here, but it certainly gives an intuitive idea. Let's consider the determinant of A minus lambda I. So here we are subtracting lambda from the diagonal entries. And all of our other entries remain the same. Now we had seen that the determinant of a triangular matrix is exactly the product of the diagonal entries. So here we have the product of our diagonals is 5 minus lambda, 3 minus lambda, 5 minus lambda, and 1 minus lambda. So this is our characteristic polynomial, and the eigenvalues would therefore be the roots of this polynomial. We set it equal to 0, and therefore we see that our eigenvalues are 5, 3, 5, and 1, exactly the diagonal entries of our matrix. So in some special cases, we can determine the eigenvalues of higher dimensional square matrices without using a calculator, but in general, using software is a better approach. Now notice in this example, the eigenvalue 5 appeared twice. That is, it was a double root of the characteristic polynomial. So in this case, a little terminology to go along with this, we would say that the eigenvalue lambda equals 5 has multiplicity 2. Since it was a double root, we would say that the multiplicity of that eigenvalue is 2. So in general, the multiplicity of an eigenvalue is the number of times it is a root of the characteristic equation. So let's consider another example. Here we're given the characteristic polynomial of a 6 by 6 matrix is the following. So since it's a 6 by 6 matrix, we have a 6th degree characteristic polynomial. And we're asked to find the eigenvalues and their multiplicities. So recall, to find the eigenvalues of a matrix, we take the characteristic polynomial. So here lambda to the 6th minus 2 lambda to the 5th minus 15 lambda to the 4th and set it equal to 0. So to solve, we could factor out a lambda to the 4th, and we're left with lambda squared minus 2 lambda minus 15 is 0. So we have lambda to the 4th, and then our quadratic can be factored as lambda plus 3 lambda minus 5 is 0. So listing our eigenvalues, we have lambda equals to 0, lambda equals negative 3, and lambda equals 5. Now we're supposed to list the multiplicity of these eigenvalues. So for our first one, lambda equals 0, we saw that the term lambda to the 4th, or lambda minus 0 to the 4th, or lambda minus 0, that factor appeared 4 times within this characteristic polynomial. So the 0 eigenvalue would have a multiplicity of 4. And our other two eigenvalues, negative 3 and positive 5, only appeared once, or their factors only appeared once in the characteristic polynomial. So these each have multiplicity 1. or these are sometimes called simple eigenvalues if they have multiplicity 1. So in our next example, now that we have this technique for constructing the eigenvalues of a matrix, let's look at an example where we find the eigenvalues and the corresponding eigenvectors for a matrix. So this is a problem of interest in a lot of applications. And again, for 2x2 matrices, this can be done pretty quickly by hand. And even for 3x3 matrices, it's not terrible. But in general, you would want to use some sort of software, say a computer or calculator, to find the eigenvalues and vectors of a larger dimensional square matrix. But just to see how this can be done by hand in a simple example, let's consider this. So to find our eigenvalues, we're setting the determinant of a minus lambda I, which is our characteristic polynomial, equal to 0. So let's look at that determinant. We have the determinant of 1 minus lambda, 2, 3, and 2 minus lambda. So the product of our diagonals is 1 minus lambda times 2 minus lambda, minus the product of the off diagonals would be 6, and this is equal to 0. So expanding, we have lambda squared minus 2 lambda minus 1 lambda would be negative 3 lambda, plus 2, and then subtracting our 6 on the end leaves us a negative 4. We set this equal to 0. So this then factors as lambda plus 1 times lambda minus 4 is 0. So our eigenvalues are negative 1 and positive 4. So that would be the first part of this problem, finding those eigenvalues. So let's take a look at finding the corresponding eigenvectors. So recall that the system we're looking at, or the equation we're solving, is a minus lambda I times some vector x is equal to the 0 vector. So we're looking for non-zero vectors for x that would solve this system, and any non-zero vector which solves this is a eigenvector. So for each of the eigenvalues that we just found, let's find the corresponding eigenvectors. So starting with our first value, let's call it lambda 1 equal to negative 1. Let's consider the coefficient matrix A minus lambda 1 times I, times some vector, let's call it x1, and set that equal to the 0 vector. So expressing this as an augmented matrix, let's consider this coefficient matrix, A minus lambda 1 times I. So that is the exact matrix that we had up here when we were taking the determinant. A minus lambda I is this matrix here. We're just taking the specific value, lambda equals negative 1. So if lambda is negative 1, that matrix has a first row of 2, 2, and the second row is 3, 3. So we can see, of course, the rows and columns are linearly dependent, which means that there is a non-trivial solution. There is some non-zero vector which will solve this homogeneous system. So by row reducing this matrix, we can see pretty quickly that this is row equivalent to the matrix 1, 1, 0, 0, augmented with the 0 vector. So we can see from our augmented matrix that x2 is a free variable, and from the first row, x1 has to equal negative x2. So for an eigenvector, our first eigenvector, let's call it x1, we could take any vector of the form x2, negative 1, 1. So one easy choice for an eigenvector might simply be -1, 1 itself. That is, if x2, our free variable, is chosen to be 1. But again, any non-zero scalar multiple of this vector will still be an eigenvector, because x2 can be any number I want except 0, because recall the 0 vector is never an eigenvector. So let's see if we can find an eigenvector for the other value. So if lambda, let's call it lambda 2, our second eigenvalue, is equal to 4, then looking at the equation, a minus lambda times I times another vector, let's call it x2, is equal to 0, could be expressed in terms of an augmented matrix as follows. So remember, this matrix that we're looking at, a minus lambda times I, is the same matrix that we were taking the determinant of to find our eigenvalues. So just substituting 4 into that matrix, we have a first row of -3, 2, and a second row of 3, -2. So again, our rows and columns are clearly linearly dependent, so we know that we'll have a non-trivial solution of this system. So performing row reduction, we can see that this is row equivalent to the matrix, let's call it 3, -2, 0, 0, 0, 0. So multiplying my first row by -1 and adding the first row to the second row, we get here. And then putting this in reduced row echelon form, we could divide the first row by 3. So we have 1, -2/3, 0, and then a row of zeros. So we can see here that x2 is a free variable, and x1 is then equal to 2/3 of x2. And so for our second eigenvector, x, let's call it x2, we could take any vector of the form x2 times 2/3 1, or equivalently, x2 times the vector 2, 3. If I take x2 instead to be 3 times x2, I can eliminate that fraction in my first entry. So any vector of this form would be an eigenvector, and if we just need one particular choice of an eigenvector, we could take 2, 3. So this example illustrating how to find not only the eigenvalues of a matrix, but the eigenvectors associated with those eigenvalues. Now in the last part of this section, we'll introduce the concept of similar matrices, which we'll see appear in our next section and throughout the Chapter 5 material. So here let's introduce the definition of similarity of matrices. So we would say if A and B are two square matrices, both n by n, then A is said to be similar to B if there exists an invertible matrix, call it P, such that P inverse times A times P is equal to B. Or equivalently, if we were to take this equation and left multiply by P and right multiply by P inverse, we would have just A is equal to P times B times P inverse. Now for this equation, if we were to rewrite Q in place of P inverse, then this equation could be expressed as Q inverse B times Q is equal to A. So that means by definition that B would also be similar to the matrix A. So for simplicity, we would simply say that the matrices A and B are similar, rather than saying one is similar to the other. So if we are interested in changing A into the matrix P inverse times A times P, which would yield the matrix B. This transformation is called a similarity transformation. So why would we be interested in a similarity transformation or similarity of matrices? Well, it can often provide an easier way to find eigenvalues of a matrix. So the following result, theorem 5.4 from your text, says if we have two n by n matrices, A and B, which are similar, then they have the same characteristic polynomial, and therefore have the same eigenvalues with the exact same multiplicities for those eigenvalues. So let's look at the proof of this theorem. So our assumption is if we have two matrices that are similar. So that means there's a similarity transformation between them. So if, for instance, the matrix B is equal to P inverse times A times P, so this is the definition of similarity, then if we look at the matrix B minus lambda times the identity, which we would take the determinant of to get our characteristic equation or characteristic polynomial for B, this is the same as P inverse times A times P, so that was the matrix B, minus lambda times the identity. But now the identity matrix I, we can think of as the product of P inverse with P. By definition, the product of those inverses would get the yield the identity matrix. So we can rewrite this as P inverse A P minus P inverse lambda P, and then I can factor out P inverse on this left multiplication, and I'm left with A P minus lambda times P. And then I can factor out the matrix P, which is being right multiplied in each factor, and I'm left with A minus lambda times the identity matrix times P. So now, taking the determinant of both sides and using the multiplicative property of the determinant, we have the following. So our determinant on the left-hand side is the determinant of B minus lambda I, so that is the characteristic polynomial of B, which would be equal to the determinant of, on our right-hand side, we had P inverse times A minus lambda I times P. But since the determinant is multiplicative, or the determinant of a product is the product of the determinants, this right-hand side is the same as the determinant of P inverse times the determinant of A minus lambda I times the determinant of P. However, multiplying the determinant of P inverse and the determinant of P, because the determinant is multiplicative, is the same as the determinant of P inverse times P times the determinant of A minus lambda I. But this is the determinant of the identity times the determinant of A minus lambda I. But the determinant of the identity matrix, by definition, is 1, since the identity matrix is the diagonal matrix with 1s on the diagonal. So we're left with simply the determinant of A minus lambda I. And this is what we wanted to establish. This left-hand side is the characteristic polynomial for the matrix B, which would be equal to the characteristic polynomial for the matrix A. Therefore, the roots of these polynomials would be identical, and the multiplicities of those roots would be identical. Now, a word of warning for this theorem, just because two matrices have the same eigenvalues does not mean that they are similar. So we've shown here that if two matrices are similar, then they have the same eigenvalues, but the converse does not hold. Just because they have the same eigenvalues does not mean they're similar. And also, word of caution here, similarity is not the same as row equivalence. So just because two matrices are row equivalent does not mean they have the same eigenvalues. In particular, row operations on a matrix will usually change its eigenvalues.